Okay, good afternoon. Let's start lecture, okay? Okay, I just have one example to go over from previous lecture, and then we'll get on to the new topic, which is applications of double integral. So this example is basically related to properties of a double integral. Okay, just as integrations of a single variable function, you do have a very similar properties for double integral. Okay. Some of them are so obvious, so I'll just skip that. But one of them that is probably like what we use for here is a so-called basically piecewise or addition or additive property. So this property, often in time, you do need to identify yourself. How would you separate this original region R into two pieces or even more than two pieces? Okay, yeah. So this one here is the so-called additive property or integration by integration by pieces. Okay. Another property I think I might as well to mention it here is basically if your function f of x or y is greater than 0, okay, over this region R, then the double integral at here will be guaranteed to be greater or equal to 0. Okay. So this is actually quite natural property. Basically, if this is region R and then you have a function or surface defined on the top of this region R, if this is the surface like a sketch I draw as I draw it here, so apparently this is greater than 0, then the double integral, one thing that we know that is basically gives a volume, the volume above the R and below the F here. So apparently, if you look at the volume at here, it's definitely going to be a positive volume, right? So that's why it's, if this is greater than 0 and this is going to be greater than 0. And if this function is greater than another function, okay, so basically this is the surface, you have another surface, for example, maybe below this surface at here, right? Then the double integral will guarantee that this double integral will be greater than this double integral. So that's another property. Sometimes you could use that to give you a good estimation from the beginning. Okay. Yeah. Okay. So let's take a quick look example. Basically, how we can make use of the first property at here. Okay. So this additive property or this integration of parts here. I started example in the previous lecture already. So basically you have three straight lines at here separating bounding a region R. So this is the region R here, and we're going to integrate any kind of function, okay, over this region R. So this is the example that you're going to have to make use of the additive property, because if let's say if we decided to integrate this thing, okay, using dy and dx, okay, this sequence at here, then according to the procedure, then we're going to have to draw a reading lines, okay, across this region R, and as you can see, the first one here has first contact here and here. Second line here, same first contact, but then a different second contact. So the upper limit is different. So basically means you're going to have to separate this region at here, okay, into two regions. Okay, so one is R1 and the other is R2. And then we can integrate this double integral to make it equal to the R1 plus R2. Okay, so that's the example of additive. Now, for additive property, most often that you have to figure out the intersection point. So then it'll help you to figure out the integration limits. Okay, for point A, which is the intersection between y equal to 2x and x plus y equal to 2. So that'll give us the A coordinates, which is 4 over 3 and 2 over 3. And for B point, this is between y equal to half x and x plus y equal to 2. And this will give us the B coordinates, okay, which is 2 over 3 and 4 over 3. Okay, so that's the coordinates for point A and point B, huh? Yeah. Okay, so now let's try to find the limits. Basically, deal with each one of the integrals separately. Okay, deal with R1 first, and then deal with R2. Okay, so let's see for R1. Okay, we just need to figure out the limits at here. Okay, this is for R1 at here. So you look at the way we draw it here. First contact is on the y equal to 1 over 2x. Second contact, it's on the y equal to 2x at here. So basically, the lower limit here is 1 over 2x, y over 2, and then it's 2x. So that's your y lower and higher limits, right? And then you will sweep this arrow line from one edge to the other edge of this R1. So basically, it goes from here to here. Okay, finding the x limit. So x go from 0 to the x coordinate for the point A, which is 4 over 3, right? 4 over 3. So that limits for sorry. Sorry. I think that this is not right. So for the point A, your coordinates should be 2 over 3, 4 over 3. And then for the B here, this is 4 over 3 and 2 over 3. Okay? Yeah. Apparently the B has to have a bigger x coordinates than the A, right? Yeah. Okay, so here, so basically from 0 to 2 over 3. So that's for R1, right? Yeah. And then for R2, okay, so look at the R2 at here. Okay, R2, y limit, lower contact, it's the same thing, half x. The upper bound for the y is y equal to 2 minus x. Okay. And then x limit, it goes from this end to this end, which is 2 over 3 to 4 over 3. So that's basically the setup for the two segments, for the two regions that are here. Okay. Excuse me, guys. Can you higher. Very high. Okay, so any questions on the application? Sorry, on this particular example right here? Okay, all good. Okay, so let's continue right here. We'll look at okay, not really a new topic, but we'll look at basically applications of a double integral. There are many applications. Okay, so I'll just give you some very basic ones that are here. Some that you actually probably already learned in the past, in the previous lecture, some other courses. Okay, but we'll use the double integral actually to illustrate some of these basic applications that are here. Okay, yeah. The first one is a very easy one. The first one here is basically try to find the area, okay, of a thin plate. Okay. So what does this thin plate basically means? Basically, let's say if I give you a region R, okay, this is a region R. Essentially, it's a flat region, okay. But I can consider this is a plate with the thickness so thin that we can literally assume it's just a flat region, right? So that's what the thin plate means. Okay. Then the question here basically is, what will be the area for this thin plate at here? Okay. Yeah. You can also use instead of calling it thin plate, you can also say that find the area of region R. Okay, that's basically a different way of putting it. Okay, so this is actually not really new because if I write down the double integral formula, okay, here's the double integral formula here. Now, if we let this f of xy equal to 1, so that function equal to 1, then this double integral becomes r dA, right? So basically it becomes this. So if I ask you a single variable here, give you a single variable dx cubed, what does it equal to? X cubed, isn't it, right? Or if I change this to anything, to a function at here, it gives me back this function f, isn't it, right? So now if I look at this double integral here, this is 1, so integration, whatever integration that is, but d followed by this a at here, so this one's supposed to give me back what? The area. Okay, yeah. So that's the idea here. So integration d anything give you that anything. Okay, yeah. So that basically is the idea of getting the area of the thin plate. Here's the formula. Okay, that's basically what you do. And the dA you treat as a euro, dx, dy, dy, dx, or use polar coordinates, right? rd, rd theta. Okay, it's the same thing. Okay, same way of doing it. So let's take a look at a very quick example. This should be very straightforward at here. Okay, let's say I have a region R bounded by two curves. Okay, so here's y equal to x, y equal to x squared, and I'm interested in the area of this region R, or this thin plate. So using the formula, your area is just a dA. So in this case here, I'll continue to use Cartesian coordinates. Let's say I choose dy dx as the order of the integration. Then the rest of the work is basically the same as the process for finding the limits for a typical double integral. So y, you draw an arrow line in the y direction. First contact, second contact give you the limits for the y variable. Then you sweep this arrow line from one end to the other end. That goes from 0 to 1. Okay. So this is how you calculate it, and you get 1/6. Okay, you carry out this calculation here. Okay, that's the area of a thin plate. Good? Yeah. That will be the first application at here. Okay. So let's look at the second application. Second application will be to calculate the mass of a thin plate. Okay. So mass of thin plate, essentially, we give this double integral slightly different, basically meaning at here. Well, I should draw it. I don't have to draw. Just draw it. Okay. If this is region R, or this is a thin plate, region R representing this thin plate, and then we're gonna define a density at here. Okay, delta. So density could be a continuous density across the region R, or could be just a constant density, maybe 1 or 2, right, across the density region R here. Okay. So technically speaking, if you're going to calculate the density, what you can do is you can basically use the approximation method. You get the mass of a small patch, right? Get the mass of small patch. Then you add up all the patches, small patches together, all the mass, small masses together, then you get a total mass. So the delta M, right, could be just simply equal to delta times the area, right? So if this is a delta area here, then the density, because it's so small, so consider it's a same across this delta A, so delta times delta A. Then you add all them up, you get the total mass. Adding them up basically means you are doing integration at here. So this essentially give you the mass property here. So the delta at here is essentially it's a function. Okay, essentially it's the original function f of x, y, except that now we're giving it a physical meaning. It's the density function now, right? Okay, so don't be confused that by the symbol here. Essentially, you're still doing double integral. The same function, but it's just a different, now different meaning, right? Okay, that's the second one, the mass of a thin plate. The third and the fourth has something to do with the average value. Okay, so let's first take a look at the first type of average. So average value of this function f of x, y over region R. If you learn statistics probability, and then there is this average concept here. So let's start from the very beginning here. Give you an illustration here. Okay, suppose that I have a data set. You have a number of samples set here. Okay, so you sample, you get this many of values here, and you calculate the average. So basically, you add them up, okay, and then you divide it by n, so you get the average at here, right? Okay. Now, the question we're looking for is, it's the average of this function, right, over the region R. So let me maybe draw something at here, and then to illustrate the difference. So let's say we have a region R at here, okay, in the xy plane. And then we have some kind of a function on the top of region R. And here is your f of x, y. Okay. So here's what we want to find it. If you pick a point inside the region R, then project that right to this to the upper surface at here. So this is basically one height, isn't it, right? That's a height. You pick another point and you go up here, so you get another height. Okay, yeah. So the idea is you want to basically find all the height, then you add them up, and you divide it by the total number, then you get the average height, right? Yeah. And that average height at here is this average value. This average value of the function over this region R. Does that make sense? Right? But the way I just said it, it's impossible, isn't it? Right? I mean, how many points inside the region? You have infinite. You have infinite number of points inside the region R, and then you have to take infinite number of heights, and then you add the infinite number of them, and you divide it by this infinite things. Okay, that's not like this finite set of here. Okay, yeah. So what we have to do is, so we have to basically try something, approximation method at here, okay, and then lead us to a more accurate calculation at here. Okay, yeah. So this is how I will derive the formula at here. Okay. So let's say I'm gonna maybe take a small area. Basically, instead of finding an infinite number of height, so we're gonna section basically this region R into many small patches. Okay. Yeah. How many? Maybe there will be n number of delta A, right? N number of delta A. So I'm gonna let this f of x, y, okay, be the height. Okay. And suppose that at this particular location, this is x of k, y of k location. Okay. Then this particular point will have a height x, k, y of k, right? Okay. So now you can imagine you have a rectangular box at here with a height which is, right, f of x, k, and y of k. Okay. Yeah. How many boxes do we have? Let's see. I have there are n number of boxes, so n number of these small patches that are here. So that means I have n number of these heights, right? I can sample out of this approximation. Okay. Then what we can do is we can say, okay, so I'm gonna add all of these heights, but it's only from 1 to n. Okay, so add, this is a limited number, right? So add this n number of heights up, add them up, then divide it by this total number n at here. So that's going to give me basically an average height quantity. That makes sense, right? Okay. Okay, so now I'm going to manipulate this expression just to arrive at the final formula. I will multiply delta A at the bottom then I had to multiply the delta A, right, on the numerator just to cancel out the denominator. Okay, yeah, so nothing changed, right? By doing so, as you can see, this n times delta A, this, so the number of patches times this small area, one patch. What does that give you? This n times A here. It should give us what?
The area?
Yeah, it should give me the area, right? It's approximately. So basically, this should give me the area of this R at here. And then let's rewrite the rest of them at here. Okay. Yeah. So that's the height approximated, right? That's a problem because you will only take n number samples here. Now if n goes to infinite, so now you from approximation to precision. So if you let n go to infinite, then this height will become the average value now. So basically this summation sign will become double integral. And the delta sign will become straight d, so area differential. Okay, differential area. So this is basically the so-called average value of the function f over the region R. Okay. Yeah. So we'll come back to this formula probably later here. Okay. Now, what's the application of this? Right? What's the application of this? So, for example, right? I'm not going to solve an example, but just to give you an example here. So let's say temperature. If you have a region, you have a thin plate, and then you can measure that you have the function of temperature across this thin plate at here. So if this is a temperature, T of xy representing the variations of temperature across the region R, and you're interested, what's the average temperature, right, across this metal plate? Okay, how do you do that? Right, this is basically, will give you the average temperature, which equal to 1 over the area, and then divided by the R, T of xy, and dA. Right, so that's one example that you can calculate. Okay. And now there's some other example. Probably you can I can write another one here. Let's just suppose f of xy here represents the distance from from a certain point, a fixed point, from any point to a fixed point. Okay. So here's one fixed point, and then you have basically, let's say a thin plate at here. Here's the fixed point P, and then you can try to calculate, from all the other points, from all the other point to this fixed point. You have a distance, right? So then you can always calculate what's the average distance. Okay, what's the average distance from all the other point to this fixed point here? And the calculation is same formula, so area and R and f of xy and dA. Right. So same idea. Okay. So this is the idea of average value of a function f over a region R, right? Okay. Any questions so far? Okay, so let's look at number 4. Number 4 will be so-called the weighted average. Okay, weighted average. Same thing. Let's start from the simple probability concept here, right? Yeah. Now suppose that we have a data set. So you have a number of basically, let's say, data points collected. Okay. Now the difference now is you also have a weighting vectors, or weighting factors. The weighting factors, basically, each data point plays a different type of impact, let's say, right, on this analysis. Some more important, some less important. So you have basically a weighting factor associated with each one of the data sets right here. Okay. Then if I need to calculate this average, not just average now, you need to calculate the so-called weighted average, of this data set, then your weighted average let's call it x bar will be W1 times x1, W2 times x2, Wn times xn, and divided by the addition of all the weights at here. So that's called weighted average. Number 3 is basically a special case of the number 4. If the weights at here, they are actually equal weight, okay, if they're all equal weights at here, then this formula will give you back this number 4, right? That total average formula, okay? Yeah. Okay, so how is that going to relate to the double integral here, right? Yeah. Now, so let's say I have a region R at here, okay, and this region R, okay, representing some kind of a thin plate, and this thin plate has a density distribution given by the delta function, delta x, y, okay. Yeah. Then maybe I should draw a 3D graph at here. So let me draw a 3D graph here. Okay. Okay. So here's region R, and it has a density delta x, y at here. At the same time, okay, you have a function f of x, y. Giving it here. Okay, so then this function f of x, y is defined over the region R. So technically speaking, if you pick a point at here, then you go up, then you have a basically value defined by this f of x, y at here, right? Okay, yeah. Now, if I put in one more information, which is the density information at here. So let's say suppose this is your x of k, y of k location. Okay, so at this location. At this location, so at this location you have a value f of x k, y of k, right? Okay. Now if I see that this guy here, okay, is weighted, okay, it's a value, right? It's data point, and this point is weighted by something else. Now in this case here, as I'll see, it's weighted by, let's say, the density at here, so delta function, okay, but delta function at here. Okay. Or maybe I should just say let's before I say delta, let's just say it's weighted by the mass, okay, delta mk. Okay, so delta mk representing the small mass around that area. Okay, so which basically means you always multiply this data point with the weight, which is delta mk. Okay, delta mk. So you have a data point, then you multiply by the weight, and this is actually literally weight. It's a mass, right? Yeah. Yes. Are the weights constant? In this case, it's actually when it boils down to single point, it'll be a one value basically, right? But when it basically changes, then this weight will be a varying quantity basically. Yeah. So you weight this function by this delta mass, and then delta mass is directly related to the density function. Right, density function. So I can literally write time the density function, and then times the delta area. So density times the area give you the delta mass. Okay, yeah. So this function is weighted by the mass, or weighted by these two together. Okay. And now if you want to calculate the weighted average, right? The weighted average. So what do? You basically add all them up, right? You add all them up, and then you divide it by the total, right? Divided by the total there. Okay. Yeah. So basically your average at here, your weighted average. So let's say use f bar at here. So that's going to be, you add up all of this single quantity, Okay, then you divide it by the additions, right? You divide it by the additions of all the weight. What's the additions of all the weights? The additional load, this is the weight, okay? Remember, huh? This is the weight at here. So you basically you add all the weights up. Okay. And then you get this weighted average, right? Okay. So if you compare this formula with this formula here, it's the same thing, right? It's the same thing basically. Okay. So now if we, and this is probably from k equal to 1 to n. Okay. So if we let n go to infinite, if you let n go to infinite, then you can literally see that this weighted average, the top one in here, the summation become double integral. And the bottom here, right? The bottom here, what would the bottom become? This is the density times the mass, small mass, one patch. You add all them up, then the double integral gives you the what? The total mass. Right? Give you the total mass. So this is the formula for weighted average for a function f. In this particular case, you had to basically be clear as what is the function that you're taking average here. This is f. And what is the weight at here? And it's this, right? It's this. Okay? Yeah. So this is basically the formula for calculating the weighted average for a function f. If you look at this formula here, and then if you let delta equal to 1, what does this formula become? Yeah, it'll become the number 3, right? Basically the average value of the function f now. Okay? Yeah. Okay, so that's good. So that's two average concept. I'm actually going to use the number 4 to derive the formula for number 5. Okay. Any questions so far? Okay. Number 5 is the center mass. Okay. So center mass is here. Okay. So center mass basically is a concept. Okay, finding a point. Okay, finding a point which is the so-called centroid. And in this case here, it's the center mass for a thin plate. Okay. And what? Oh, that's crazy. Okay, yeah, take a break. Hi, I'm in the library of 317 for lecture, and then the projector all of a sudden just turned it off. I mean, it's not turned off, it's not projecting anymore. Yeah. Yeah, just take off, and then the control panels, there's no response when I try to touch the screen. Library 317. Yeah, it is. Rigid. Not yet. Oh, there's a flicker. Okay, one comes back. Yeah, there it comes back. Okay, good. Okay. Okay. All right. Okay. Okay. Thanks. Okay, back to life. Let's continue on the center mass study here. Okay. Yeah. So center mass basically is a location where it's a center, right? But what really does it mean, right? What does it basically really mean as a center? Okay, yeah. Let's say you have imagine there are infinite number of small masses, okay, on this thin plate right here, and then the thin plate, let's say probably as described by density delta, right? And then literally at a different location, right? At different location, you will have a different small mass quantity if you multiply with the density. Okay, yeah. So the x bar, y bar basically represents is actually the weighted average. The weighted average in the x direction and the weighted average in the y direction. When you incorporate the mass concept, right, into this consideration. Okay, yeah. It's not just the average of x coordinates, y coordinates. It's a weighted average in a mass, in a sense of mass at here. Okay, how heavy in this direction as you're going along the x and then going on the y, right? So basically, your x bar here, right, is a weighted, your x bar and the y bar. It's a weighted average concept. Okay. So now I'm going to make use of the formula from number 4, okay, to derive this x bar, y bar. So I'm going to let f, okay, the function f of x, y equal to x. Okay, I'm going to let f equal to x at here. And then I will plug in this function f into the previous formula. So what do we get? We basically get 1 over the mass, right? And then you have a double integral here. Then you have this function f at here, which is x currently, and then time the weight. The weight is delta xy dA, okay, times the weight. So this will be the after the substitution in here. This is what would you get. So now you look at this formula here. So you are weighting this x coordinates with the mass, which is the weight, right? Then you do the total double integral, and then you divide it by the mass. So this one here give you the idea, that give you the concept of the weighted average. So this is basically give you this x bar at here, x bar. Now, that's the weighted average. So same thing, if you're going to calculate the weighted average for the y coordinate, and then all you need to do is, right, you just have to let f function here equal to y. Then it'll be, okay, this formula. So these two formulas give you the weighted average, okay, for basically we give you the centroid, or the center of the mass. Okay. Good? Yeah. Incidentally, I want to point out a quantity inside this formula here, okay? Now, if you only look at this portion here, only look at this portion, okay? Only look at this portion here, and we can actually define this my as this first one in here, and then we can define the mx as the second one in here. Okay, we can define two functions, mx and my. Okay. So what are they? They are also a physical quantity, actually. Okay, they're also a physical quantity. So let me illustrate a little bit here. Okay, let's see if I'm gonna take a small patch at that location. So I'm gonna take a small patch at that location. And what is the mass for this small patch? So let's say for this little location is delta mk. So that's a small mass at that location. So delta xk yk times delta a. Okay, so that's your small mass there, right? Okay. Not dynamics or statics. Anyway, so there's a concept called moment, isn't it? Right? A moment equal to what? Equal to the force times the distance, right? Okay. So now I'm gonna extend the moment concept. I'm gonna create another concept called mass moment, not the force moment. It's called the mass moment. So what is a mass moment? You use a small mass times the distance, then you get a concept called mass moment. Is that right? Yeah. So if I use this small mass to time this distance, in this case here, this distance what? It's the y, right? It's the y of k. Okay. So basically, if you use this delta mk times y of k, so this is a mass moment. Okay, mass moment. About which axis? About this x-axis, right? Yeah. And you can imagine you do have another mass moment concept, which is delta mk times what? xk, right? Yeah. So that's also mass moment concept. And this is a mass moment for single small mass, right? For single small mass. If you add all of the small moments up, mass moment up, then you get this. You get this my and mx at here. Is that good? Yeah. So now these two at here, there's a name for it. It's called first moment of the area. Well, because we're talking about thin plate at here, so that's why we can say this is a moment of the area at here. Okay. This is basically the first one here is with respect to the y-axis, and the second one here is with respect to the x-axis, okay, respectively. Okay. So first moment of the area. When we learn triple integral, when we learn actual 3D subjects instead of just a thin plate. And we'll have a similar concept now. That will be the basically first moment of the not the area anymore. It's going to be the first moment of the mass, basically. Okay. In the mechanics material, are you guys learning mechanics material? Oh, next semester. That's right. In mechanics material, when you learn next semester, and there's somewhere in that course, there will be concept basically involving this first moment area. So the area sometimes is also called the cross section. Okay, cross section. So when you cut a cross section, you're left with the area, right? Yeah, and you're interested in basically what's the first moment of the area. Okay. So that's the fifth application at here, center mass. Yes.
Does this moment have a direction like force or not? Because the force doesn't, or the small area doesn't, the small mass doesn't have a direction like force.
You don't have to consider the direction, but literally, if you're talking about moment, yes, you do have a direction, right? Yeah. But in this case here, I don't think you need to consider direction because we're talking about two special directions. One is x-axis, the other is y-axis. But you can definitely relate to your arbitrary, basically, axis, right? You can see this is the mass moment to arbitrary axis. Yeah. Good thinking. Yeah. Okay. So number 6, as you probably can guess, it'll be the moment inertia. Okay. So moment inertia. More precisely, because we're talking about thin plate. Okay, which is literally just a cross section we're considering. So this will be the moment inertia of the area. Okay, yeah. And sometimes this is also called second moment of inertia. A second moment of area. You see the fifth here? This is the first moment of area. Then the formula we're going to derive will be the second moment of area. Okay, so that's the difference. You actually can literally argue: is there a third moment, fourth moment of the area? Yes, there is. Okay. If you learn the probability statistics, there is also first, second, and there's also upper higher order of this average concept. Okay. Yeah. Okay. So moment inertia, I'll start from very beginning here. Okay. Let's start from the mass. Okay, and then looking at the moment inertia. And you learned mass, and you learned that basically from first year or even high school. Okay? So if I use a very simple language, yes. Okay. Is that good? Yeah. So if I use a very simple language, mass, what is it? It's what? How hard it is to impart translational motion, right? Okay. So I would call that mass. Okay. And mass is sometimes you think it as a point mass kind of concept. Okay. So hard is it to impart translational translational motion. And then this moment of inertia concept. Okay, so MOI. A moment inertia is a concept that has to be associated with an axis. Okay, so it has to be with respect to an axis. If you separate the moment inertia with aside from axis, then it has no meaning in here. So then what does moment inertia basically mean? So if you use a similar language as I just described for a mass, can you see that what should we see about moment inertia then? It's how hard it is to impart what? Rotational type of motion. Okay, so that's basically what moment inertia, the difference in it here. Okay. Good? Yeah. So this gives you an idea. If you want to spin a really big guys, it's much difficult than it to spin, right? So, and which is why, for figure skating, it's for slim and smaller size, right? That'll help. Yeah. So, how do we calculate moment inertia here? Okay, so I'll still start from very beginning in here. Okay, yeah. So I'm gonna, as I said, moment inertia is always about certain axis, right? So now I'm talking about the moment inertia with respect to the origin. So what does the origin basically means is if I'm gonna draw something in here, okay? Let's say if I'm gonna draw an object here, okay? Then I'm talking about moment inertia of this object with respect to an axis passing through that origin right here. Okay, so I can use the z-axis to represent that rotational axis. Okay, so that's basically what I mean at here by respect to the origin. And the results we derive it here, okay, can also be called polar moment of inertia. So the results derived here, okay, it's also called polar moment inertia. Okay, so let me draw another graph here. So I'll start with a point mass. So you have an m right here. So this is a so-called point mass. And point mass meaning you ignore its volume, right? It's so tiny. You know, everything is concentrated on that one single point. Now let's just suppose that this mass at here is traveling at a linear velocity v, right? Linear velocity v. And then what happens is, maybe this is your initial location at here. So it will, let's say travel to the next location up to here. So that's the difference. That's the motion at here. So it's a curve. You're traveling on a curve here. So initially, let's say it has a radius of r, and it will travel for a very small angle delta theta at here. Suppose that this is so small, so I can think of from here to here, right? I can think of this from here to here. It's actually an angular motion, so it goes right in the angular type of motion. So then your velocity, right? This is your velocity here. Then if I neglect the vector sign here, so this will be the speed value. This will be speed. So I can relate the speed approximately to the quantities r and the delta theta. So speed equal to distance divided by time. And in this particular case, it travels this much distance from here to here. So how much distance is that? It's r times delta theta. And how much time did it take? Let's see, delta t, right? So that gives me the velocity between the velocity and theta value at here. And of course, if you let this delta become infinitesimal small, then your velocity will basically become r times d theta over dt, right? And d theta over dt, we often use a different symbol to represent this d theta over dt. Yes, right? So we use omega here. So that's your angular velocity, or angular speed in this case. So that establishes a simple relationship between the linear velocity and the angular velocity here. And now let's go back to the kinetic energy. So kinetic energy. Kinetic energy for this point mass is 1/2 mass times velocity. So 1/2 mv squared. And I just established a connection between the v and rw. So I'll replace the v with rw. So this quantity out here, I will expand it. I'll group this r with m and single out this omega square here. So your kinetic energy has an alternative writing now. Instead of 1/2 mv squared, it's 1/2 mr squared times omega squared. And now I will define a quantity for this mr squared. So define this quantity mr squared. Then the kinetic energy will equal to 1/2 I naught times omega squared. So different expression for the kinetic energy. Now what we just defined it here, this I naught equal to mr squared. This is basically the moment of inertia, of the point mass with respect to a axis, going through origin. And I teach robotics in the 4th year, and I actually felt that when it comes to the moment inertia, it doesn't, it never hurts to write down as much as possible. because there's also always a relativity type of concept at here. Okay, relative to what? So this is basically the moment inertia point mass with respect to the axis going through origin. Because you see here, the r, right, is the distance from the m to the axis going through this origin at here. Okay, yeah. So this is actually kind of a little bit connection to the so-called second moment in area. Now remember that first moment of the area is what? We have this so-called mass moment concept, right? You have this mass times the distance. But if you look at this one here, is what? It's the mass times distance square, right? So using this one here, you're gonna get basically this so-called moment inertia, which is a second moment area in this case here. Okay, yeah, second moment area. Okay, so this one here is a single quantity, huh? It's a single. It represents the moment inertia for a single point mass. Single point mass. Okay. Now, if I really wanted to do is, here is a thin plate represented by region R, and I'm interested in what's the moment inertia of this region R with respect to the axis passing through the origin here, right? Okay. So then I can make use of approximation concept. So I will take a small area at here, and this small area has a small mass, right? Has a small mass. So delta mk equal to delta the density times the small area, okay? Times small area, and the small area is very small, and I can literally think it's a point mass. Then the moment inertia of this small mass with respect to the origin, right, I can write it down as, let's say maybe ik equal to delta mk times rk squared, right? So that's the moment inertia for that one little patch with respect to the origin. Okay. If I need to calculate the total moment inertia, so then what do? We add all of this up, right? And then you want a precise quantity, and you let the total number go to infinite. Then the addition becomes summation. So your total moment inertia will be integration in here. Okay, like this. So let's use x, y, and then dA. Okay. So this is the total moment inertia here. So total with respect to origin. Okay? Yeah. So a little bit circling around here, and we end up with the formula which for the moment inertia with respect to the origin in here. Now this one here, you need to simplify this a little bit because it's a mixture of r and x and y. So we might want to put everything into the same variables. R at here represents basically it's the distance, okay, from the mass to the origin. If this is one location to the distance, so the distance r squared is what? It's always x squared plus y squared. So that's your x squared. That's your r squared, right? And then time delta, and then dA. Okay. So this is your moment inertia about origin. Let's use a subscript IO at here to represent this moment inertia. Good? Yeah. Okay. So that's number 6, right? Number 6, you can easily extend this now. If I ask you this different question, what's the moment inertia of this thin plate with respect to the y-axis? What will be the formula? So with respect to a y-axis, this is x, this is y. So use the same formula, but not the same formula. Use this formula to sort of as an analogy to derive this moment inertia here. So you see here, this is the formula. This is basically how you get the moment inertia with respect to origin, right? From here times this distance r. If with respect to the y-axis, then you go from here times what distance squared times this portion here, right? This portion. And this portion is what is this portion? This is basically xk, right, in this case. Okay? So that mass times xk squared give you the moment inertia about the y-axis. Then you add all of them up, you get Iy, okay, equal to x squared, right, times delta xy and dA. So similarly, we're talking about the x-axis then. So this will be y squared dA. Okay, yeah. And if you have even any other arbitrary axis, then all you need to do is to get the actual distance from that particular point, right? Axis to the axis. Okay. So good? Yeah. Yes. So yeah, moment inertia is always about a certain axis. That's basically number one thing you need to remember, right? Yeah. And when you calculate, then it's always about basically the one small mass times the actual distance from this point, this mass here, to that actual axis of rotation. Yes. What is it? That's right. Yeah. Yeah, because when you go from here to here, that's the distance, right? And that distance is x-axis in this case. From here to here, it's the y-axis. Okay. Yeah. Good. Number 7. Actually, there's no number 7. So, okay, that's it. Let's look at example. Okay, so I'm gonna calculate this quantity here. Okay. Suppose that we have a very thin disk, which is a circular disk, with a radius of a at here. Okay, so there's a disk, circular disk here, of a radius a, and this disk will try to spin about an axis illustrated at here, and it's trying to spin around this axis with angular speed omega. Okay. So I'm going to try to calculate here is what's the moment inertia, okay, with respect to this, let's call this axis of axis C or C prime with respect to C prime axis. So what will be the moment inertia about that axis here? Okay. Yeah. And this axis basically goes through a point, any point, in this case any point, doesn't matter, go through a point on the circumference at here. Okay. Yeah. So this is a general problem. In this case, you actually had to formulate the problem a little bit in order to be able to do your calculation at here. Formulate the problem basically means you will have to try to establish an x coordinate system, then you put everything into the coordinate system accordingly, right? Okay. So this is what we're going to do. We'll establish xy coordinate system here, and then suppose that this is your thin plate at here, and then where would that rotation axis now? It will be right here, this z-axis, okay, perpendicular to the paper, and your plate will try to spin, okay, around this origin, okay, like that, and we're trying to get the moment inertia of the thin plate with respect to the z-axis. Now in this case, I'm going to give you another quantity here. So let's say suppose the density is a constant It's 1 across the whole thin plate. Okay? Okay. So let's do the calculation here. In this particular case, I guess you need to identify what formula to use, right? Yeah. So I only have 3 at here in this case, but which one? This one, huh? Yeah. So it's about the origin, so we need to use this formula here. So let's write it down. So the I at here, okay, equal to x squared plus y squared, and then delta function and dA. Right, that's how we're going to calculate this moment inertia. Delta is 1, so I can neglect that delta now, then just this one. Okay. So right here, then you're basically left with a double integral problem, right? Okay. So when you do this double integral, before you start to jump into it, basically means, oh, I'm going to try to find the x limit and the y limit, right? Because this region R here is what? It's a circle. So instead of using Cartesian, you actually should consider, what's the other one? Polar. Okay? Yeah. So let's use the polar coordinates. Okay? Polar coordinates saying x equal to r cosine theta, y equal to r sine theta. Then I'm going to replace the x and y with these two expressions. So r x squared plus y squared, that actually will left with r squared. So because r squared cosine theta squared plus r squared sine theta squared, take out the common factor, that cosine theta squared. Anyway. And then the dA at here, right? The dA at here, polar is what? R dr d theta. Very good. Okay. Yeah. Next step, find the limits, right? Find the limits. So finding the limits, follow the procedures, huh? Follow procedures. For polar, starting from origin, you draw an arrow line. Okay, you draw an arrow line across this region R. Okay, across the region R here. Any arbitrary rating lines across the region R. First contact point give R mean. Second contact point give the R max. So R mean seems pretty easy, which is 0. The R max, unfortunately, depends on where you draw it, right? It's apparently R max is not a constant. So we had to figure out the R max at here. So really depends on where you draw this arrow line here. So you draw it here, then there's always a theta associated with that R max, with that arrow line, right? Okay. So the whole point here basically means, what is this quantity? Basically, this is your R max you're looking for. What's the expression we're looking for here? As I mentioned in the previous lecture, most probably in this kind of question, you're going to have to use a very simple triangle trigonometry related to triangles at here. Okay. And here I can do is I can connect this point to the other side of the circle here, and use your basic geometry, and you should know that this is a perpendicular relationship, right? Okay. So now you have immediately you have what? You have this right triangle here. And what's the length of a hypotenuse? What's the length from here to here? Huh? 2a, right? Good. And you're looking for R max. So apparently your R max, that quantity, equal to let's cosine theta equal to R max over 2a. So R max equal to 2a times cosine theta. Okay. This is how you find your R max, and then you put it here, okay, for your R max. Okay. Last step, to find the limits for the theta angle. So then you start to rotate this reading line, right? From one edge to the other edge, which basically the two edges sandwiching this circular region here. So it's pretty obvious, one from the bottom and the other is the top, right? The top. Now this is where things could be different, depends on how you count this angle theta at here. Okay, how you count the angle theta. Okay. So I want to hear from you first. What will be the limits for theta? Pi over 2 to what? Okay, negative pi over 2 to pi over 2. Okay, that's one way. That's good, right? Because you're counting this way. So from here to here is negative pi over 2. From here to here is pi over 2. Okay? Yeah. That's fine. Okay, that's fine. What will be an alternative counting for the pi? So what you have to be clear is which one is the lower, which one is the higher, right? In this case, which is the lower? This got to be the lower, isn't it, right? And this has got to be the higher one. So it has to go from this one and then up to here, okay, to finish the sandwich, to the cover, the sweep. Now, if you want to be consistent, basically, let's say for this particular vector, how do I count the angle? I could count it like this, all the way from the beginning to the end. Is that good? Which is what? From here to here, how much angle? Huh? From here to here. Am I right? It is, eh? Is it? Yeah, that's right. Yeah. And then you keep going from here, keep going up to this. Basically, you go all the way up to this. Okay, that's a little bit. So, how much from here up to this is what? 5 pi over 2. Okay? So, alternatively, this angle here could be 3 pi over 2 to pi over 2. Okay? Yeah. Yes?
Could you also draw it differently since it didn't give you the exact coordinates? Draw it from 0 to pi?
No. The counting here is very important. You have to be consistent. Consistent basically means like the second one, that's what I call consistent. You start from one location, right? You always go counterclockwise. So for the first edge to the second edge, counting the total angle. And the other consistency is the first one, from negative pi over 2 to pi over, because it's still consistent, because you're counting here negatively from here to here, right? And here to here it's positively. So that's also consistency. So you cannot basically create your own conventions to get an angle here. That has to be the conventions everybody that stick to. Okay? Yeah. Is that good? So now once you get this, the rest of the work are basically integrals. Okay? I'll finish the integral in the next lecture.